our plate is we need to get a coordinate plane onto our circle as well, because everything we've done so far has included the circle and the coordinate plane together. So what we need on our circle, you have a circle because you have a plate, is we need to create an x and y axis with the origin going through the center of the circle. So what can we do to our plate to create an x and y axis? Fold it in half, okay? So we're going to fold our plate in half, and then in half again, right? So that eventually, now my plate is very old, so you'll notice it has lost all its curvature, which for this is actually nice. But you guys can like stuff your plate in your binder, set it under books at home, and it'll flatten out after a while, okay? But so eventually, you'll fold and you'll fold again, so you get a nice x and y axis going across your plate. And you will actually want to outline the x and the y axis. I don't want to give away all my top secret information here. But like so, okay? See, x, y axis. Okay. All right, so I'll put it up here. I promise it will get flatter, so the slight frustration you have, just deal with it. It'll be okay. Oh, you know what? I don't have to draw a circle, you guys. Watch. I can just make a circle. Yeah. Not white. All right, so you should end up with a circle like this. Now, I'll give you a little preview here. Basically, all the work we're going to do with the paper is going to end up on that inner ring of your circular plate, but you're going to be doing a lot of writing out on the edges here at each of those points, okay? So like each of these represents a special point to me, and I'm going to label that point out here on the edge, okay? So you want your x and y axis to extend all the way to the very edges of the plate, and we're going to focus on the circle part in here as our unit circle. Okay? I've had mine for like 4 years. Yeah. This doesn't have to be in any certain order, okay? Just on the back of your plate, okay? We're going to write a couple of key information pieces. Some of them have to do with some geometry knowledge we're supposed to have that we saw in the last couple days' notes. And then others of it has to do with some of the trig stuff we've learned and how that's going to relate to the circle. Okay? So on one side of my plate, I want to make sure that I can put some information about some special triangles. So what's one type of special right triangle that we've talked about? Okay, 45, 45, 90. So if I have a 45, 45, 90, somebody tell me the pattern that we're supposed to know that these side lengths have. Alex. Okay, good. So there's something here, and that's something times rad 2 for the hypotenuse. Okay. Are we all good with that? Okay, our other special triangle is our 30, 60, 90. Somebody else tell me the pattern I'm supposed to know that exists between the measures of the side lengths in this right triangle. Jenny? Okay. Mm-hmm. Good. So we all remember these patterns either from geometry or because we've used them over the last couple of days, right? All right. Now, we're going to come back. Actually, we're not going to come back. We're going to do it right now. Here's what I want you guys to do right now. Next to these triangles, I want you to determine what each of the legs of the right triangle would be if the hypotenuse was 1. So in a 45, 45, 90, if the hypotenuse is 1, what are the side lengths? This should be similar to the homework that you did over the weekend, right? And in a 30, 60, 90, if the hypotenuse is 1, what are the different side lengths. If you're not confident, you can do stuff on a separate scratch paper, whatever, if you're afraid that like you don't want to write it on here yet and get it wrong or something, or just be willing to erase. But right now you can work by yourself, with a partner, whatever. What would the side lengths be if the hypotenuse is 1 in each of those triangles? Uh-huh. Perfect. So she said that she got rad 2 over 2 because in order to get the side length from the hypotenuse, she had to take 1 and she had to divide it by rad 2, right? Because there was some mystery number that had been multiplied by rad 2 to get 1. So we're trying to work backwards and say, okay, I'm going to divide by rad 2 and undo that. Now, technically, when you divide 1 by rad 2, you get 1 over rad 2, and that's where she explained that to rationalize the denominator, we'd multiply top and bottom of that by rad 2, and that's where we would end up with root 2 over 2. Is everybody okay with that idea? All right, somebody new. Answers and explanations for the other. Yes, Julia. Uh-huh. Good. 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 So again, same idea. Normally, to get from the short leg measurement that you know to the hypotenuse, you would times it by 2. So if you have the hypotenuse, to get back to the short leg, you would divide by 2. Once you know that the short leg is 1/2, the longer leg of the triangle is that number times rad 3, and 1/2 times rad 3 would give us rad 3 over 2. So is everybody okay with this? So we're comfortable with the patterns, and what's going to be important to us is this arithmetic. So why is this arithmetic going to be so important? The other thing we have to make on the back side of our plate is this list of how we figured out sine, cosine, and tangent play into this idea. Okay? So our trig functions. And I'm only going to list here the sine, the cosine, and the tangent, assuming that you guys could then figure out the cosecant, the secant, and the cotangent by just doing what? Not the inverse. You have the right idea, but the wrong word. Reciprocal. Yeah, reciprocal. Okay? At least he's giving an answer. All right, so we originally said that you find the sine of an angle by putting together what side lengths of a triangle? Opposite over hypotenuse, right? So we did opposite over hypotenuse. Then we translated that to the coordinate plane with our circle on it. And so instead of calling it opposite over hypotenuse, what did we call it? Y over R. Good. Okay. Then we have this same relationship for cosine, okay, where cosine of the angle was adjacent over hypotenuse. Or when we looked at the coordinate plane, it was x over r. Okay. And then finally, our tangent function. In a triangle, we labeled it as opposite over adjacent. And on the coordinate plane, that meant y value over x value. So this is just a summary of stuff we already knew, right? So the reason I'm pointing this out, when we put it on the coordinate plane and we talked about the circle, did the size of the circle matter when we were finding the sine, the cosine, or the tangent of an angle? No. It was like these guys over here, right? It didn't matter how big you made these, because once you put them in a fraction as a ratio, the ends were going to cancel out, and you would just be left with the other things, right? So if you made the circle bigger, the end number would be bigger, but it wouldn't matter because it gets canceled out when you do sine, cosine, or tangent. So remember in one of the homework problems, or when we were talking about radians in our notes, we said when we talk about radians around the circle, we're going to assume that the circle just has a radius of 1, because we don't need those extra factors that we have to keep canceling out every time we do a sine, cosine, or tangent. Do you guys remember us talking about that? So we just plugged in 1 for r, because the r wasn't really any different when we built our sine, cosine, and tangent. It didn't matter. And we called that the unit circle. So what you're creating right here on your paper is the unit circle. So in our unit circle, one small change is going to happen. If this is the unit circle, when I call it a unit circle instead of just any circle, what am I declaring about the circle? The radius is 1. So now you might see why your teacher just made you do something with triangles that have a hypotenuse of 1. Okay? Now, if I make the radius 1, this has some significant impact on the sine, the cosine, and the tangent values. And let's see what that really means. And remember, this means it doesn't only work in the unit circle. It works in any circle because those extra factors would cancel out. The unit circle just helps us see the numbers without the extra factors right away. So if we take this information over here, and we look at it with respect to the unit circle. So remember, in the unit circle, the radius is 1, like you guys just said. What does that mean about the sine of any angle in the circle? The sine is going to equal what? If the radius is 1, and it doesn't really matter what our radius is, so we're going to make it the simplest number we can, which is 1, what does that then say about the sine of any angle? Yeah, it's just going to equal y over 1, which is just y. So that's kind of crazy. That means if I know the y coordinate at that position on the unit circle, like if someone says 32 degrees, if I knew at 32 degrees on the unit circle what the y coordinate was, I would already know the sine of the angle. That's what that is telling me. Okay? That the sine and cosine are not just related to two sides of the triangle, but because we're going to call the radius 1, it's actually the x or the y coordinate at that point on the unit circle when you put it on the coordinate plane. Okay? So that's why you have your plates, right, that have circles on the coordinate plane. We're going to try and figure out what those coordinates are so we can basically just memorize some x and y coordinates. Why do we want to memorize the coordinates? Because the coordinates really are the sine or the cosine of that angle. Okay? So the cosine of any angle, okay, so think about unit circle, the radius is 1, this is x over 1, and it's just x. Matt?
So then, y would always be less than 1.
Yes. Okay? Which makes sense. So Matt's saying, wait a minute, this means y is less than 1. Do you guys know why he's saying that? It could actually equal 1 in certain positions. But why is he saying that y is always less than 1? Eric? Okay, so that gives us another implication, means sine can't exceed 1. But how did Matt know that the y is not going to go past 1? Hannah? Good. Okay, it makes sense because of that, Matt. So you're like, wait a minute, the biggest this could be is 1. Remember when we went back here, we were trying to put some stuff in our calculator and some people were getting errors and stuff like that? And we talked about doing the inverse sine and how I wouldn't let you put a number bigger than 1 when we were in the calculator doing the inverse sine because how could this be bigger than 1 if it's opposite over hypotenuse? So yes, that does immediately mean that y is not going to exceed that value of 1. Okay? It also means the same thing for x. Right? And when we look visually at our circle, we'll see how that happens as well. Now the tangent doesn't really change. It's still the y over the x value. Which means for tangent, you're either going to memorize a whole nother set of numbers and know the tangents by heart, or you're going to be like Miss Dahl with her lack of memory space that we all know so well, who has to continuously divide out things to find tangents, like the y coordinate and the x coordinate. Okay? All right, is this okay for a good summary of information? So this is what we already knew, and this is just kind of clarifying that, since it doesn't matter and we can make the radius equal to 1, that really means the sine and cosine are the same as an x or a y coordinate on the circle, and then these are going to help us actually figure out those numbers in a unit circle because we made the hypotenuse here 1. Okay, so these calculations are going to help us on our circle. Okay? So looking back at your circle, we are going to make this the unit circle since the radius doesn't matter. So there are a few points we can label right away without the help of any triangles or protractors or anything like that. Okay? Right here at this position. Okay. How many degrees am I at that position? 0 or 360. We don't really know. So in degree world, okay, this can be labeled as 0 degrees or 360 degrees. Now, again, I'm going to show you my plate because I'm going to be very clear about this for organizational purposes. Each of these things right here is going to be labeled with a degree and also a radian and also a coordinate pair. So my advice to you as you're labeling things on your circle, label outward. Don't label in a clump because what if it runs into your next angle that we want to mark on our circle? Okay? So I'm going to put the degree measurement and the radian measurement here, and then I'm going to put the coordinate out here. So I'm going to end up writing into the ruffles of my plate a little bit organizationally. Okay, Eric? Yes. I would just use the circle that's basically already drawn. Sorry, let me clarify. I would use this as my circle right here. The circle that already exists on your plate. The inner. Okay, like the distinct circle. Okay? It's all right. All right, so in degree world, this position is either 0 or 360 degrees. Okay, and I'd write kind of small. Okay, and again, we're going to label in degrees, we're going to label in radians, and we're going to put an ordered pair. Don't put it all like this. You're going to run out of space for your other angles. Allow it to go out to the edge of your unused portion of your plate. Does that make sense? So we're going to label in the roughly section. Okay, are we good? All right, so what is this in radian world? Okay, so either 0 still or 2 pi. And what would this be as an ordered pair? What is that point? If we've declared that the radius size doesn't matter, so we're going to make this a unit circle, then this is the point 1, 0. Where am I getting 1 from? It's the radius of the circle. Why is my circle allowed to have a radius of 1? Because I made it a unit circle, and I was allowed to do that because we saw that even as the circle got bigger, since we were always putting one triangle side over another triangle side, those extra factors canceled out, so they were just creating extra factors for us. We don't need them. Let's put 1, and then we don't have to cancel anything out. Okay? All right. Up here. Position in degrees. 90. Or negative 270. We're going to go in the positive direction around our circle. So the negative part we're actually not going to label on here because then we could just have infinitely many angle labels on here. So we're only going to label once around the circle in the positive direction. But then you have to understand the other ideas in case someone gives you the information a different way. Okay? What is the radian measure at 90 degrees? Pi over 2. Okay, now remember, this is not an ordered pair. This position in degrees is called 90 degrees. This position in radians is called pi over 2. And what would be the ordered pair up here? 0, 1. And I shouldn't go out. I should really just go up above. But I don't have any more board space. Okay? You guys can write small. You know what I'm saying? Trying to keep it all in line because we're going to put an angle here and here and here all around the circle, and you don't want them to blend together. You want them to stay. And at the end, you can go through and highlight and color code so you can see which ones are which, and it'll work out. Okay? All right, so what I want you to do in your groups right now is I want you to label the other 2 points that are on where the axes meet the circle. Okay? Okay, check your work. Points are labeled. Yes, we include negatives. Even though 1 is the radius of the circle and the radius would always be considered positive, when we put it on the coordinate plane, remember, just like what makes 60 degrees, the sine of 60, different from the sine of the triangle that we're using in another quadrant of the circle, is all about what we label as negative and positive. So the coordinates here are negative 1, 0, and here is 0, negative 1. All right, so let's see how many people have put together all of this information. So remember Friday, okay, that I said you're going to know stuff automatically, right? Like someone's going to ask you the sine of 60 degrees, and you're going to say root 3 over 2. You're just going to know it. It's going to be there, right there, okay? So here's how people know it. Patterns. Every 90 degrees, what do you notice about the coordinates that we came up with? They all contain what? 0 or 1 in the positive or negative form. It would depend on some direction. So I do have to have some understanding of direction. Okay, so let me ask you guys this. What is the sine of 90 degrees? 1. Why is the sine of 90 degrees equal to 1? Turn your plate back over. Okay, because the sine of any angle is equal to the y-coordinate. So if the y-coordinate at this position is 1, then the sine of 90 degrees is 1. What is the cosine of 90 degrees? 0. Okay. What is the sine of 3 pi over 2? Negative 1. The sine is the y-coordinate. And the cosine of 3 pi over 2 is 0. Okay. What is the tangent of 3 pi over 2? See? Negative 1 over 0, which is undefined. See, I have to do that every time. I have to think it through. Some people just measure, like, there and there, it's undefined. Okay, totally a personal kind of thing. Or they memorize. Cody?
How do we get cosine of 90 is 0?
Cosine of 90 is 0. So turn your plate over, look on the back. See where it says the cosine of an angle equals x over r? But then when we made the unit circle, that meant x over 1, and so the cosine was equal to x. So the cosine of 90 degrees is 0 because 0 is the x coordinate at 90 degrees. Okay? All right, so do we see a pattern happening there? All right, so for that everything that's related to 90 is going to be a 1, a 0, positive or negative, we figure out by position. And that sine is the y coordinate and cosine is the x coordinate. And tangent, you're either going to build those later and memorize them, or you'll divide every single time to figure it out. Okay? All right. But now these aren't the only angles that we're responsible for. Okay? So the first thing we're going to do, we're going to look at 45-degree angles. So what I need everybody to do is, so it's pi over 4 in radians, good. We're going to actually use a triangle to label where this position is so we can understand the lengths of the triangle. So first we need to get a triangle. Rather than using a protractor 4 different times to measure 45-degree angles in 4 different triangles, we're going to use the circle to do it for us. So what I would like everybody to do is cut out one green circle. Okay? We need to give the circle a way to be divided up into angles that we want to measure. And right now our focus is going to be on figuring out about 45. So what we've done is we've found out in these positions the coordinates based on everything that's a factor of 90. It was easy because we knew the radius of the circle. 45 is a little harder. We get about where it would go, but then we got to figure everything out. So what we want from this is we want 45-degree angles. So we start with a circle that has how many degrees? 360. If I fold it in half, I'm now looking at 180 degrees. So I should fold it in half again. I know that the edges aren't perfect, you guys. It's going to be okay. I know you guys are like freaking out about this. Okay, so I'm at 90 degrees, and then I should fold it one more time in half. Okay? Now, I'll crease it good, and this means when I unfold my circle, I will see a center section with a bunch of 45-degree pieces. Fair enough? Okay, what I want you to do is take your pencil, and on those creases that are on your circle, you need to make one of them an x-axis, just like you have an x-axis here. So I'm going to declare one of these to be like my horizontal x-axis going across my circle. Okay? Now, what we want is this. We want every triangle that would be on our unit circle that has a reference angle of 45 degrees. Now, there is only one angle on my unit circle that is 45 degrees. But somebody give me an example of another angle on my unit circle whose reference angle is still 45 degrees. 135. Okay? Why is 135 an angle whose reference angle is 45? Eric? Because it's 45 degrees away from the x-axis. Somebody give me another angle that would have a 45-degree reference angle. Raven. 225, because it's 45 degrees past 180. Somebody give me another angle that has a reference angle of 45 degrees. 315. Now, we could technically keep going forever, but we would just keep landing at those 4 spots. But I really want to use this to identify those 4 spots. So you're basically going to cut out from your circle the triangles that would exist at the 45-degree, 135, 225, and 315-degree mark. So let me break that down for you a little bit more. There's a line right here that goes 45 degrees above the x-axis. You want that you're going to cut a triangle out right there of your circle. Let me finish explaining first because I'm going to make your cutting a little simpler. We're going to shortcut, okay? We also want, so that's our actual 45-degree angle. Then there's one over here. That's our 135-degree angle that's also 45 away. Then there's one down here That's our 225, that's 45 degree away. And then there's one down here that's 315, that's 45 away. So here's what I would say. You guys, instead of having to cut out 4 triangles to make your life easier, here's what I would do. I would cut along one of the lines above the axis that's 45 degrees, one below, and then cut a straight line to connect them. It's going to look like little butterfly wings or something when you cut it out. You get what I'm saying? So once you cut it out, it's going to look like this. You're going to have this giant green piece with the x-axis running across it that represents 2 triangles, each triangle with a 45-degree reference angle. Okay? Then you're going to do the same thing on the other side. So again, my advice is cut a 45-degree above, a 45-degree below, and then you can end up cutting out this like semicircle, and then just connect those two so that it's triangles and not circular at the end. So then you'll have this going on over here. Whether you do it that way or not, you need to get these 4 triangles that are 45 degrees away from the axis. Okay, all of these have 45-degree angles here. And then you are going to put them onto your plate. Okay? Yes. Okay. So, let's see. Mine are not the right colors because the Astro Brights I had available to me this time were different. So eventually on your plate you will have this beauty. Looks just like what I drew up there kind of. Okay? This kind of idea. Okay? Again, I know you might think the cutting not worth it, whatever. It's going to help you remember, oh, first I can identify 45-degree angles. There's 4 places this happens. Those 4 places should have something in common. Okay? So glue it onto your plate once you get that happening. So your plate should look like what I have up here, drawn up here on the board. Okay? So we have our 45 degrees. Somebody who remembers, Eric, please, or wrote it down, tell me what this is in radians. Pi over 4. Good. Oh, man. Isn't that like early? Oh, no, it's late start day. I forget. All right. That's okay. We will leave it right there. So tomorrow when you come in, you have to know about 45s. What are you going to remember?